Okay, thank you everyone for joining. As Michael mentioned, I work down at Johnson Space Center. I'm Mr. Design Engineer for the Gateway program, and so I'll be talking a little bit about Cislunar related things and one application of FreeFlyer in doing so. So some of the motivation behind this study that I've been working on is we have a lot of missions going to cislunar space. Namely, these are the ones that I'm most close to. The Gateway mission, which is going to an L2 southern near rectilinear halo orbit. And then, as we saw in the previous video, Artemis 1 went to a distant retrograde orbit about the moon. So these orbits are unique in that they rely on the Earth and Moon's gravity simultaneously in order to exist, in order for the path to exist. And so we need to develop some special strategies or new types of strategies to design trajectories in this regime, just given how sensitive the dynamics are. So one of those types of tools that we want to develop is how we can take trajectories from a lower fidelity model, say the circular restricted three-body problem or the four-body problem, and transition them up to a higher fidelity ephemeris model. So that ephemeris model is going to include the effect of the sun, our non-spherical lunar gravity or non-spherical Earth gravity, and then the non-circular orbits of these bodies as well. And we can throw SRP in there as another one. So all of these different forces are what are going to be most realistic when we're actually flying in space. So we want to be able to model them for our trajectory. And so we can utilize a targeting or differential corrections strategy to transition from our lower fidelity to our higher fidelity model. So what does this look like? What does targeting look like? So some of you may be familiar with this, but I'll just kind of go through a really basic example of what this is. So it's essentially an iterative numerical method to help us solve for a set of constraints. So whether this is position of velocity continuity, altitude, delta V, and we can use the variations on our state of the spacecraft in order to achieve those constraints through a numerical iterative process. And it's implemented in a number of ways. So one way is multiple shooting, which we're going to talk about in this presentation today. Another one is a two-level targeter. I did a presentation on this a few years ago in FreeFlyer, and then I believe Luke talked about co-location earlier in this expo. So all of these, there's a number of other ones as well, but all of these have advantages and drawbacks. With multiple shooting, we need to have derivatives associated with all of our constraints and free variables, and then but we're dealing with inverting a very large matrix every time we have an iteration. A two-level targeter kind of takes that and breaks that down a little bit so that matrix isn't quite as big. However, the derivation of the two-level targeter is a little bit more involved than it is a regular multiple shooting problem. And then co-location is sort of a different beast in itself. So we're going to talk through multiple shooting, and I'll just show a really basic example here of what actually sort of a representation of this looks like. So if we start with a low fidelity trajectory in, say, the three-body problem, for example, shown in blue here, we discretize this trajectory to a set of nodes called patch points. And then we take each of those patch points and we move them into the higher fidelity model, and we propagate them forward for the same amount of time. We can see, as we would expect, since the model is different, the trajectories are going to, or each of these arcs are going to be discontinuous. So what we want to do is develop a method to make them continuous. So we can parameterize these as a set of state vectors, or in time as well, since we're working in ephemeris model. And what we want to do is iteratively update the position and velocity associated with these states to achieve continuity of all of them along this arc. And ideally, at the end, we will yield a trajectory arc that has the same basic properties as our original trajectory that we found in the lower fidelity model, but with the more realistic gravity and force effects on it. So in order to do this, FreeFlyer's optimization tool actually makes this really easy to set up and sort of manage the problem. Specifically, being able to specify analytic constraint derivatives is really nice because it helps with convergence. You don't have to worry about if I'm doing finite differencing on my derivatives, what's my perturbation value have to be to accurately represent the derivative. And you know, if you have to use a higher order finite differencing technique, that can slow down each of your iterations in your targeting problem. Additionally, the bookkeeping of all the derivative information, which is typically one of the more challenging things associated with doing one of these multiple shooting problems. The optimizer object makes it really easy to do that. You can specify your constraint, you specify your free variable, and then you just put the derivative in. It's just that straightforward instead of having to figure out, carrying around what all the indexes are and how that Jacobian matrix is supposed to look. Additionally, it has different types of solution methods in order to handle different types of scenarios. So different solvers, you can use SNOpt, IPopt, or you can just do a minimum norm if you so choose. Now, this is all important because the cislunar dynamics are chaotic, and so we need to have a robust way to transition these solutions because it's going to be fundamental to the design process of any trajectory within cislunar space. So taking a look at just a basic section of the code here, I'll walk through some of the advantages that I mentioned in the previous slide. So we have a procedure, I've developed a procedure that we can calculate. We're going to look at an altitude constraint for that matter. And so we pass in the trajectory object, so the trajectory segment, and then we'll calculate the constraint and the derivatives relative to that constraint. So if we can set the value of the constraint, and we can specify a string value which will be attached to that constraint, so that when we try to set the derivatives, we can just call that string and the associated free variables with that, which happens down here. So we set we call the constraint that we're talking about, and then the free variable associated with that constraint for the derivative that we're going to set. And then we can do that, and then it's all set in there. So you don't have to worry about indexing of where in the Jacobian these are all supposed to be placed. Additionally, we can do time of flight as well. So we can set the derivatives of our altitude with respect to the time of flight and the actual epic time in the ephemeris model as well so if we want our problem to be variable time as opposed to fixed time, we can do that as well. So we'll look at two examples of this process working. So we have the first one, which is looking at a heteroclinic connection between L1 and L2 on the Earth-Moon system. So this heteroclinic connection is essentially a transfer that uses no deterministic delta V to depart our orbit and arrive in our new orbit. And this type of transfer was used by the original Artemis Themis mission back in 2010, 2011. So the example that I'm going to be using is starting at an L2 quasi-halo orbit and then going to an L1 quasi-halo orbit. And the initial guess that I've computed has been found in the circular restricted three-body problem. So this model assumes that the Earth and Moon are both orbiting around their common Berry center in circular orbit. So it has no non-spherical gravity. It doesn't account for the sun. However, the ephemeris model that I'll be using accounts for solar gravity and then non-spherical gravity effects of the moon, and also obviously the ephemeris positions of the Earth, Moon, and Sun. And so within this targeting problem, I'm only going to be enforcing position and velocity continuity between all the nodes. And what we'll notice here is that I use a bunch of segments along each of the destination and departing orbits. This is an attempt to keep the problem a little bit stiffer so that we maintain the geometry of the transfer a bit better. So once we run the corrector, I won't show it running because it's just essentially shows a number counting down to show that it's converging. It produces a trajectory in our higher fidelity ephemeris model. You can see that sort of starts to wrap around our initial orbit here, and eventually it will traverse from the L2 side of the moon to the L1 side. Now, this is nice. Again, the power of Free Flyer is that we don't have to code up or create any of the force model itself. Free Flyer is really good at that, and so we want to leverage those capabilities. And then now with the optimizer in there, that makes it a little bit easier to set up the targeting problem in order to do this. So the second example I'll look at is a ballistic lunar transfer. And these are involved in a four-body problem where we have the Earth, Moon, and the Sun. And these types of transfers help us get out to the moon by leveraging the solar gravity in order to get out there. and they can significantly reduce the cost, the delta V cost, in order to access the moon. There have been a number of missions that have leveraged these type of transfers thus far. The Grail mission back in 2010, both Grail A and B use this type of transfer to get out to the moon to measure the moon's gravity. And this is the trajectory of both of those is shown here on the right-hand side. The Capstone mission, which just successfully arrived into its near rectilinear halo orbit, the same orbit that the Gateway is going to be flying in. It just arrived there using one of these ballistic lunar transfers. And the KPLO mission actually is going to be arriving, I believe, later this month into, all right, maybe it's next week, into its orbit about the moon using a ballistic lunar transfer. So it take a little bit more time. We're looking on the order of, let's say, a month or a few months, as opposed to, a week or so for a direct transfer to the Earth. So this is in contrast, I guess, to Artemis 1's trajectory, which took a more direct route. So they take longer, but they're more advantageous because you have significant propellant savings once you get out to the moon. Additionally, just a sort of an interesting story is the Capstone mission. They ran into a few hiccups along the way where they lost contact with the spacecraft. And because they had this longer time of flight where they could work out some of their problems, they were able to recover the spacecraft and continue the mission. Had they had the same issues going on a direct route to the moon, they probably would have lost the mission just because of the quicker turnaround they needed in order to fix whatever was going on. So another advantage of these, even though longer time of flight, it can still be advantageous. So the initial guess we're going to use is constructed in the Bicircular FourBody problem. And this makes an assumption that the Earth and the Moon are orbiting in circular orbits about their barycenter center, and then the Earth-Moon barycenter center is in a circular orbit about the Sun. And this is good because it's a more simplified model, but includes all the gravity effects from the Earth, Moon, and the Sun. So we can construct these in a fairly straightforward manner. So in addition to position and velocity constraints along all of our nodes, we are going to constrain the initial node to be at a periapsis at an altitude of 150 kilometers relative to the Earth. And what this is doing is it simulates a state just after a translunar injection burn. So just after we're departing the Earth from a orbit, the idea is to sort of simulate that within this correction strategy. So demonstrating that not only we can do position and velocity, but any other constraints that you can formulate under the Sun. And the destination for this is going to be an L2 quasi-halo orbit, which you can see on the bottom right-hand side of the screen. So after running the corrections process, it converges on a continuous solution that departs the Earth and arrives at the Moon. So on the left-hand side is the Sun-Earth rotating frame. We can see our trajectory departs, flies out into deep space near Sun-Earth L2, and then arrives into our quasi-halo orbit. On the right-hand side, you see the Earth-Moon rotating frame that it sort of circles around our quasi-halo orbit for a little while towards the end. And I stacked up a few revolutions around the quasi-halo orbit so that it kind of keeps the problem a little bit stiffer. We maintain the geometry of the trajectory we want to get out there, and then maintain the geometry of the trajectory once we're into the orbit that we so desire. Okay, so just a few concluding remarks here. So the methodology developed is essentially transitioning from a lower fidelity model, whatever that may be, to a higher fidelity model that we can leverage the features of FreeFlyer. Additionally, the optimizer object that has been put in FreeFlyer recently really helps from a bookkeeping aspect and from a targeting process to set up the targeting problem to get these trajectories into a higher fidelity ephemeris model that we can do different types of analysis on later, and use it as a reference for if we want to do Monte Carlo analysis, if we need to do station keeping, various different types of higher fidelity analyses that are required. Additionally, we showed that this framework works for two different types of cislunar transfer trajectories. So with that, thanks for your time. Thanks for having me, and I'm happy to take any questions if there are any.
All right, thanks, Brian. a few questions we have here. Can you talk about some lessons learned that you have from your experience using FreeFlyer in cislunar space, just as more and more students and people start planning lunar type missions?
Yeah, sure. So one of the interesting things is FreeFlyer was originally developed with looking at classic orbital elements and very much Earth-based orbits, but in the recent years, they developed a lot of great tools in there to do some of the cislunar or the libration point orbit analysis. So I know, for example, the Gateway mission design team, we rely heavily on FreeFlyer for doing just about all of our station keeping analysis. And it's a great tool for that. The features in there that you can use to look at different aspects when we're trying to figure out why our station keeping isn't working for certain scenarios, it's great. This functionality of transitioning from lower fidelity to higher fidelity is sort of a cornerstone of the design process in general, when you're stepping up in fidelity. And then for the cislunar problem, you have to look at design of a reference trajectory a little bit differently than you would, say, a low Earth orbit or even a GEO for that matter. So I would say it's a great tool when you want to do some of that high fidelity analysis for doing things in cislunar space.
Awesome. You talk about, we had a great talk from you just now about stepping up the fidelity, and I get how that makes, I get it kind of conceptually, and you talked, a little bit, some of the how-to, but from like a workflow and data perspective, how does it work for you to connect different tools for low fidelity modeling and then transition that information into FreeFlyer?
That's a good question. So right now, the Deep Space Trajectory Explorer, which is another product that we're working on here at AI Solutions, I'm leading that team, and that sort of focuses on the lower fidelity design aspects of designing these cislunar orbits, or these trajectories and orbits and all that kinds of stuff. We've developed it such that we can hook directly into FreeFlyer, so it's integrated into the Deep Space Trajectory Explorer itself, which is really great because you're not having to handle different types of files and reformatting things so that you can read it into FreeFlyer. It's all sort of a seamless transition. And so the idea here is this has been, what I've shown today has been developed as a standalone tool, but the idea is to integrate it within DST as well. Another point I'll make is that the way we have set this up to import data from wherever you're working is just a standard JSON, a JSON format. And so the JSON interface in FreeFlyer makes it really easy to take all the information from all of your patch points that you have, bring it into FreeFlyer, and then perform this targeting process. So that, in terms of the workflow, I hope that sort of answers the question you're getting at.
Yeah, absolutely. We had talks earlier today about optimal control and the new feature in 7.8. Can you think of any applications for being able to leverage that optimal control capability in cislunar analyses? Absolutely.
So the optimal control stuff that was talked about a little bit earlier, that's it's based pretty heavily, or the collocation is the method to do a lot of that optimal control stuff. And effectively, this is just another way to, that formulation of optimal control using collocation, that would be another way to solve this same problem. So you have a trajectory in low fidelity, you want to step it up to get it to higher fidelity. You could use collocation and optimal control in order to do that, particularly if you have a low thrust spacecraft, because that collocation tends to work better for that scenario than just a more ballistic or impulsive, high thrust spacecraft.
Gotcha. Cool. And then from our FreeFlyer developer team, what new optimization features or improvements would you like to see in future releases of the software?
That's a good question. Put me on the spot. I think
if we fully solve the problem and everything's perfect, that's okay too.
No, so actually one of the challenges that we're working with right now is that The state transition matrix is propagated behind the scenes in free fly, which is great. And that's really the cornerstone of being able to get these analytic derivatives for the Jacobian. One thing that I would like to see, I guess this is less optimizer related and more propagation related in free flyer, but being able to propagate the variations on the epoch time with respect to state in free flyer, because right now we have to do a approximation of those. And given some of the sensitivities of these trajectories, it can be challenging to pick the right method to do that estimation. So effectively what it is if you have a variation on your of your epoch of your state, so your Julian date, how does that affect downstream? How does that affect the state of the spacecraft? Being able to pull that information out that's numerically integrated would be useful to me.